The systematic nomenclature for alkyl halides is the same as that for alkanes. And we simply name the halide as a substituent. You list it in the name according to the usual numbering and alphabetizing rules. The names of the halogens, if they're substituents on alkanes, are listed here. Fluoro for fluorine, chloro for chlorine, bromo for bromine, and iodo for iodine. So a simple example would be a molecule such as this, where the chlorine and the bromine are substituents, and so this would be named as 3-bromo-2-chlorohexane. A lot of the simple alkyl halides have common names that are still widely used, particularly for commercial chemicals. And we can see a few examples of those here. And the way the common names work is almost as if these were ionic compounds. So this is a methyl fluoride. This is ethyl bromide, and so on. You can see the other examples here. This is an isopropyl group, isopropyl iodide, tert-butyl group, tert-butyl chloride. Methylene compounds, where we have a CH2 group, are named as methylene and then the name of the halogen, even though there are two of them. So this is methylene bromide. There are some interesting compounds where you have three halogens attached to one carbon. These are historically known with a nomenclature that ends in form. So this is chlorine derived, so it's chloroform. There's a corresponding bromoform and iodoform, which are one carbon and three bromines and iodines. Vinyl compounds are also named this way, as are allyl compounds, you can see here. But it doesn't take too much for the compound to not be able to be easily given a common name of this sort. And so you see that these examples down here are simply systematically named. In addition to the names of the compounds themselves, we also classify alkyl halides according to the type of carbon the halogen is directly attached to, and that's what's shown here. So for instance, there are essentially 5 categories: methyl, primary, secondary, tertiary, and vinyl. So some simple examples here are if the halogen is attached to a methyl group, it is classified as a methyl halide. If the halogen is attached to a primary carbon, meaning a carbon attached to one other carbon, then that's correspondingly a primary halide. If the carbon bearing the halogen is a secondary carbon, it's secondary. If it's a tertiary carbon, it's tertiary, and so on. And then if the halogen is attached to a double bond of some sort, these are classified as vinyl halides. Alcohols are essentially organic derivatives of water. You want to think of an alcohol as a water molecule where one of the hydrogens has been replaced with an alkyl group. The nomenclature is exemplified by a couple of these examples here in the center. And the way the nomenclature works is you find the longest carbon chain in the molecule that the hydroxyl group is attached to, and that determines the base name. So if we look at this example here in the middle of the slide, the hydroxyl group is attached, for instance, in this compound, to the longest chain we can find that the hydroxyl group is attached to is 3 carbons. So this is a propane-derived compound. IUPAC says we drop the final E of the alkane name and replace that with an OL to indicate that the hydroxyl group is present. And then we indicate the location of that hydroxyl group. Since this is a 3-carbon chain, the hydroxyl group is on carbon number 1, and so this is a 1-propanol, and then the other substituents are named in the usual fashion. This is a methyl group on carbon number 2. So by that nomenclature, if we look at the neighboring compound here, we can see that we have a 4-carbon chain that the hydroxyl group is attached to, and that hydroxyl group is on the second carbon from the end. So this is 2-butanol, and so on. There are also common names, again, that are widely used because these are abundant compounds, very commercially important. And so often you will see the names derived where the alkyl group is named followed by the word alcohol. So ethanol, which would be IUPAC's name, could be called ethyl alcohol. Methanol could be called methyl alcohol. 1-propanol would be propyl alcohol. 2-propanol would be isopropyl alcohol because that's an isopropyl group, and so on. There are a lot of very important alcohols that are available commercially and are widely in use, and some of them have common names that are so widely used that you should commit them to memory. So for instance, allyl alcohol, this is an allyl group attached to that. Crotal alcohols, they're both cis and trans crotal alcohols. A crotal group is a common name for this 4-carbon chain where the double bond is in the middle of the chain. Benzyl alcohol contains the benzyl group, which is the CH2 and this aromatic ring. Phenol is a derivative of benzene, and you can see that compound here. The others that you should commit to memory are ethylene glycol and glycerol. You'll see these compounds again. Amyl alcohol probably isn't worth memorizing. So while alcohols are organic derivatives of water, you can think of amines as being organic derivatives of ammonia. And they are derivatives where 1, 2, or all 3 of the hydrogens of ammonia. So here for reference is ammonia NH3. And these are also given primary, secondary, and tertiary classifications, but it's used differently than we did previously with the alkyl halides. With the alkyl halides, we were focused on how many carbons is the carbon that the halogen is attached to, how many other carbons is that carbon bonded to. This is used differently. The primary, secondary, and tertiary simply refer to the number of alkyl groups directly attached to nitrogen. So if there's 1 alkyl group, it's a primary amine. If there are 2 alkyl groups replacing 2 of the hydrogens of ammonia, it's a secondary amine. If all 3 of the hydrogens of ammonia are replaced, it's a tertiary amine. And then finally, there are ammonium ions where you have a tetravalent nitrogen. And in that form, the nitrogen has to bear a positive charge. So those are going to be ammonium ions. And there are organic derivatives that are organic derivatives of the ammonium ion, where 1, 2, 3, or all 4 of the hydrogen atoms of an ammonium ion are replaced. And these are also cations. For primary amines, you name the R group and add the suffix amine to the nomenclature. So for instance, here we have a methyl group with an NH2 attached to it, so it just becomes methylamine. Ethyl group with an NH2 ethylamine, and so on. Here's a benzyl. The pH here, by the way, is just an abbreviation for that aromatic ring that we saw on the earlier slide. If you have more than 1 alkyl group, you would indicate that with the appropriate names of those groups or the appropriate replicating prefixes. So here we have 2 methyl groups attached to nitrogen, di for 2 of them, methylamine. Here we have triethylamine. You can have different alkyl groups attached to the nitrogen. A couple examples here where we have a methyl and an ethyl. We would list them alphabetically. So it's ethylmethylamine, not methylethylamine. Here we have 3 different alkyl groups. We have a benzyl group, we have an ethyl group, we have a methyl group. That's the alphabetical order, benzyl, ethyl, methylamine. And there's a few other examples here that follow that same pattern. Another way to name primary amines is to name the NH2 group as a substituent. And the cases where you would want to do this is when there's a higher priority substituent that dominates the name. Alcohols, according to IUPAC, have a higher priority than do NH2 groups. So if you have both an NH2 group and an OH group in the molecule, IUPAC says we're going to derive the basis name of that compound, the ending of this, as if it were an alcohol, and the NH2 group becomes a substituent. So by that, using that as our guideline, we have a 2-carbon chain. It's an alcohol because the alcohol has priority over the amine. The amine is a substituent, so this is essentially an amino group substituted onto ethanol. By definition, the carbon that the hydroxyl group attached to is carbon number 1, so that amino group is on carbon number 2. We don't need a locant here that says it's 1-ethanol. It is by definition 1-ethanol. This compound would number from the right and go to the left. So 1, 2, the alcohol is on carbon 2, so it is a 2, it's a 5-carbon chain, pentanol. The amino group is on carbon number 4. This one is chiral. It has 2 chiral centers, and so we would have to indicate the configurations in front of the name in the usual fashion. Here's an opportunity for you to practice determining RNS configurations and confirm that these are correct. If we have those groups on a ring, again, the alcohol is given priority, and that's going to be carbon number 1. We would count around the ring in such a way to give the other substituents the lowest numbers possible. That places chlorine on carbon 3 and our amino group on carbon number 4. It's another alcohol example. It's a 3-carbon chain, so it's actually a 2-propanol. We would number that carbon chain from one end to the other. We have an amino group on carbon 1 and an amino group on carbon number 3, no matter which way we count. This last one's an interesting example because we have a substituted amino group here on this chain, and the chain itself, the longest chain that contains the alcohol, the longest carbon chain is that one. And if you look closely, that's a 4-carbon chain. So we have a 4-carbon chain that the alcohol is attached to. So the basis of our name is a butanol for the 4 carbons, and the alcohol is given priority, so that carbon that the hydroxyl group is attached to would be carbon 1. So this nitrogen-containing group is on carbon number 3. But how do we indicate that there's something actually attached to that nitrogen? It's not just a simple amino group with an NH2. And IUPAC uses a capital letter N to indicate substituents attached to the nitrogen. And the way this is read is 3-N-methylamino, meaning the methyl group is on that nitrogen, 1-butanol. And you notice the parentheses so that we understand that that N-methylamino is its own group. There are many cyclic compounds that contain nitrogen in the ring. And they have common names and systematic names according to IUPAC. There are some common names here that you, again, should commit to memory. Not all of the ones on this slide, but I'm going to point out the ones that you should. Pyrrolidine, piperidine, pyridine, morpholine, and pyrrole are structures and names that you should memorize. You will see them from time to time throughout the course, and they're common chemicals that are used in a laboratory for various things. IUPAC allows you to use those names in nomenclature, so you can name things as, for instance, a substituted pyridine and that sort of thing. I mentioned earlier that if you have a tetravalent nitrogen, it's going to be a cation, an ammonium ion. These would be components of salts. There would need to be a counterbalancing anion. And so ammonium salts have some sort of ammonium ion, some sort of positively charged nitrogen, and some sort of anion, often a halogen in the examples that you see here. The names of those ammonium salts is named the same way you would name a substituted amine, where you simply name the alkyl groups, but in this case followed by the word ammonium. And so if you look at these examples, the first one, we have 4 ethyl groups. Tetra is 4, tetraethyl ammonium, and then we name the anion in the usual fashion, bromide. You can have different groups. This one has a methyl, an ethyl, a butyl, a propyl. You put them in alphabetical order. It's butyl, ethyl, methyl, propyl, ammonium, and then you name the anion. You don't have to have 4 alkyl groups. There can be hydrogens in the tetravalent nitrogen. And so here we see we have two alkyl groups, two hydrogens, but the positively charged nitrogen. And so this one would be ethyl methyl ammonium chloride. Finally, ether nomenclature. There are two ways of naming ethers. One is IUPAC's nomenclature, where you consider the larger alkyl substituent as the parent chain, and you name the shorter alkyl substituent and the oxygen together as what's known as an alkoxy substituent. Or because a lot of these are very commonly used as solvents in a laboratory, they have some common names. And often the common names are just simply to name the two alkyl groups followed by the word ether. And so if you look at those examples here in bold are IUPAC's nomenclature. So this first example would be named as a methyl derivative, and then that methyl group has this methoxy group attached to it because it's a methyl oxygen, so it's methoxymethane. The longer alkyl group becomes the parent. So the second example, this would be named as an ethane derivative, and again we have a methoxy group attached to it. We don't need locants in those compounds. Diethyl ether, the most common laboratory solvent we use, is by IUPAC's nomenclature, it's ethoxyethane, and so on. You can see those. So there's some common names here that you should commit to memory. One is just diethyl ether, or ether. If you hear an organic chemist refer to ether, that's the one they're talking about. Tert-butyl methyl ether you will use in lab from time to time. Tetrahydrofuran you should know the name of. You should also know furan. And finally, you should know the name of anisole. That's a common name too.